Cellular phones. I've named this lecture using the US style of address for this sort of telephony, in honour, really, of the invention of cellular telephony in that great country, the United States of America. But for those of you who are watching in other parts of the world, let us switch to mobile phones, which I will also use. You could also call them a cell, if you like, and I'll try and bring out some of the other names in the lecture. I've already suggested to you that cellular telephony, cell phones or mobile phones were invented somewhere, but probably the word invention isn't exactly what springs to mind. Even I'm, who's quite sort of broad-minded about such things, when the word invention is mentioned, have a tendency to think of some lone eccentric sort of tinkering away in a basement, creating a device. This is the great Wallace and Gromit, of course. And although such inventions are quite heroic, artifactual inventions, the inventions that we have been talking about in this series aren't always of that form. I mean, we have been talking about some theoretical inventions, for example. Physicists would call them theories, and they're sort of really ideas or inventions made of pure thought. Error control coding was a good example of that. I gave a lecture on that a month or so ago, and that was exactly a thought invention. I don't think mobile phones even fall into that category. Cellular telephony is really what we would call a protocol invention. And a protocol invention, they're not what the public imagine inventions to be at all, but I think they're equally fascinating. They're agreements between people of ways of doing things, like a standard for doing things. What's so interesting really about cellular telephony is the sort of complex nature of the agreements that make things work. So I want to sort of emphasise that a bit in this lecture. The category of things that we're discussing here is certainly an invention, but it's not an invention as we might ordinarily know it. And as some evidence for that, I scoured Wikipedia, who sort of brought my attention to two cartoons. I've got one of them up here. The first one was actually from the UK. It was shown in Punch magazine, and it shows a couple actually with what are imagined mobile phones, and rather amusingly, one of them is, well, talking to her lover, I think, so sexting, as we would say now, and the other one was amazingly having a go at online gambling, so another one of those ideas. This one, however, is a German cartoon, and it dates from 1926, and it shows an imagined scene in Berlin where everybody has a phone. Now, you know, I don't know whether you would call that an imagination or a nightmare. It's a rather complicated cartoon and runs over 2 pages, and I think it's meant, I don't speak German well enough to really understand it, but I think it is meant to be implying how brilliantly sophisticated Berliners are compared to the inhabitants of Munich. But nevertheless, the idea is there. So, the basic idea of using radio waves to connect people with mobile phones is probably as old as radio waves. So not an original plan. But the problem with connecting everyone with radio waves is it enters quite a few practical difficulties. So in principle, how could we make a mobile phone? Well, easy really. We'll just amplify your voice and we'll convert it into an electrical signal, and then we'll amplify the electrical signal and we'll whack it out into a bit of wire, and you'll stick another bit of wire up somewhere over there and you can hear me. And then we'll do that. That's called a simplex system, where we're sharing transmission and talking down one bit of wire. If we wanted to talk simultaneously, we would have to do that the other way around, but let's keep it simple for the time being. And the immortal formula that governs the wavelength of transmissions at a certain frequency is up here on the screen. We always seem to remember it as c equals f lambda, even though if we're going to compute lambda, the wavelength, everyone I know always writes, oh, c equals f lambda. No, so that means lambda equals c over f. For some reason, we always remember it this way. And that's the problem. So if you take, say, the low end of the human voice, 400 hertz, and if you just amplified that and whacked it into a piece of wire, you might say, well, I want the antenna to be some fraction of the wavelength. I mean, normally a wavelength, but let's be generous and say a tenth of a wavelength, something like that. You end up with a mobile phone that has an antenna or piece of wire dangling out of it that's probably a couple of 100 kilometers long. Highly impractical and certainly not handy. Handy is the German word for mobile phone, by the way. So obviously we're going to have to do something to get around that. And that's indeed what an early mobile phone system did. The first thing it did was modulate the transmission onto what's called a carrier. So that's a high frequency waveform, a high frequency wave. If you're using a high frequency wave, then F goes up, lambda comes down, and we can get down to antennas that are the sort of thing that we can hold in our hand. Well, a big hand in the original phones. So that was the first innovation. That in itself is not innovative. I mean, obviously anyone who's used a shortwave radio or a marine VHF will have used that principle, a very simple idea. They're point-to-point communication systems designed to connect two people to each other. What we want to do with mobile telephony, of course, is be able to call anyone on the public switched telephone network, the PSTN, and we want to be able to call each other. And that implies knowing where the other person is so we can route the call properly. Now, why do we need to know where the other person is? Because we're using quite a high wavelength, and if we're using quite a high wavelength, that tends to be associated with short range, and so we cannot directly transmit to the person we want to talk to. They might be the other side of the world, so we're going to have to get to a radio tower fairly quickly, and mobile telephony is all about line of sight communication. So we're going to use quite high frequencies to connect to a set of radio towers. So the situation looks much like this, where we're going to have it looks approximately like this. We're going to have a set of, I've drawn them as radio towers. They're sometimes called base stations. And anyone who lives pretty much anywhere on the planet, you only have to look up to see these things. And they are the towers with which you are communicating when you lift up your handset to talk. Now, so far so good. Don't think we've done anything particularly original, and we haven't actually really exposed the essence of cellular telephony at this point, because this is merely the sort of system we might have for highly customized radio telephones, they used to be called. So the busy industry corridors in the US and the UK used to have a few of these masts dotted up and down those corridors, things like the M3 in the UK, and people, when they were in range of a big tower, they would be able to speak to people, and when they weren't, they couldn't. The important thing about cellular telephony is there's lots of these towers, and you traverse through them, communicating with the tower, and, as we say, handing over from one tower to the other tower. So one tower sort of radiating out this wave in a circular pattern, so we could think of the coverage we're going to get from this as a set of concentric circles. Now, circles are a bit awkward, so in most of the literature you will see those circles replaced with hexagons. And hexagons are very nice because they appear to pack together. Now, just so there's no confusion here, radio waves don't suddenly traverse in hexagons in the cellular world. The hexagons are a thought device to help us think about coverage. And they're used by people called network planners, sort of rarefied group of people. There aren't many network planners on the planet. And very often you'll see in the literature these things are sort of coloured to indicate that each cell operates on a separate frequency. And in order to avoid interference, we want to make sure that we don't have adjacent cells operating on the same colour. So the idea here is that cells that are adjacent to each other will not share the same colour. So in this case, I don't think it takes much counting to realise that there are 7 cells here in a cluster. So this would be a system. If I, say, coloured the cell marked with a question mark with cyan, then that would be a frequency reuse factor of 7. And undergraduates in this field are routinely tortured with calculations about how big the cells can be and what the frequency reuse factor can be. In practice, it isn't always 7. Sometimes you'll find people using sort of square type arrangements, so it's under 7. And sometimes you'll find people being more conservative and they'll maybe going out to the second ring of this, so the frequency reuse factor is higher. How big are the cells? Well, that varies as well, and one of the features of cellular telephony is it makes it quite easy to insert cells within cells. So a small cell, a microcell, might be under 2 kilometres long. A picocell might be 200 metres. There are also femtocells. I haven't come across many of those. They're under 10 metres. And somebody told me there are even attocells, which are 1 to 4 metres dense. That's an incredible thought, isn't it? That here I am at the podium here in my own little cell. There's somewhere up in the roof here is a special cell designed only for Richard. Sounds, well, if I'm going to pun on the word cell, it sounds like a sort of Kafkaesque situation. Now, you'll also see the model here is that the antenna is in the centre of the cell and it is working on a particular frequency. That's not the only mental model. There's another mental model where we have directional antennae, and they are on the corners of these cells and they're beaming into the cells. So I'll talk a little bit about this later because it's a sort of feature of 5G, these beams. They're not uniquely associated with 5G, which is the latest standard in mobile telephony, but they are, so 4G has some directional capabilities in it, but 5G is really going to make big use of these things. Now, clearly in this example, this cell here, the user is being sort of hit, if you like, with 3 possible beams on different channels. The handset looks at the possibility for reception. It makes constant measurements of the signal strength, and it picks the strongest one, if provided that the strongest one has capacity to have it, and then you connect to that. And then as you wander about through these cells, you get the handset, and the infrastructure associated with it is constantly monitoring it and saying, you'd be better off now being served by this other cell, and it initiates a handover process. Usually it's called a hot handover, which sounds very exciting, but what it actually means is it opens a connection with the next cell in the process, and at the right moment, having established that connection and done a whole load of chit-chat between them, which I'll talk a little bit about later, the idea is that your signal is moved from that cell to that cell without you noticing. So that's the cunning bit. Now, in a way, it's not cunning at all. It's all using very proven and very well-known technology. So I want to sort of emphasise this aspect a bit, which is, and I don't want to be dismissive, but the fact is that there was nothing really very original in the first mobile phone, and there's nothing particularly. I can hear engineers howling at me as I say this, but I'm not meaning to be rude. But what I mean is, cellular telephony is a great example of putting together reasonably well-proven technologies in a system that works, and there's nothing to be embarrassed about that. I think it's something to be proud of. It's a system that works, and the reason it works is because it's tried technology. It's not bleeding edge technology, as we would call it. Right, a bit of history. So, if you're not very familiar with the mobile phone world, you are about to enter the sort of febrile world of acronyms. And here are some examples of the hand devices, or hand machine actually is what a mobile phone is called in Chinese. Xiaoji, I think, is the word for it. Hand machine. Great idea. I loved having a hand machine. On the left-hand side is what's called the first generation mobile phones, and these were analog. So they were like sort of fancy walkie-talkies. And the first probably handset was the Motorola Dynatec, which I've illustrated here. It was thought up by an enterprising guy called Martin Cooper. And there's lots of sort of folklore around the Dynatec. If you've seen, what's the film with Gordon Gekko in it? Wall Street. Yes, Wall Street. Wall Street, he uses one of these phones to harangue one of his junior people from the beach, if I remember rightly. Highly impractical, highly improbable. I doubt if there was any mobile reception on the beach in those days. But anyway, and there's lots of folklore that has arisen around the Dynatec, of which one, which is told on YouTube by Martin Cooper, is that having developed it at high speed, he then called a press notification of this phone and promptly dialed his main competitor on it, who at that time wasn't able to produce a handheld phone and could only produce car phones. Needless to say, his main competitor denies this story, but it's a good story. So 1G, first generation phone, it does not have any data capability, this first generation phone. It is strictly a voice device, and it's like a sort of fancy walkie-talkie, which changed channels as you moved cells. When we go to 2G, right, then this is the first digital voice phone, and it has a little bit of data capability, really not very much. This is where SMSs, the text, was invented. The way I heard it was an afterthought from Nokia. They had this bit of spare capacity, and they thought, well, let's do this text thing. Not sure it will be very popular, but let's have a go at it. And the rest is history. It sort of got picked up, but firstly by the youth movement, and now we all text each other, or the modern alternative. So that's 2G. And then in 3G, this is when we start to see the iPhone, and 3G is really data starts to come to the fore. But it's still a bit of a lash up, and we've got a voice channel and we've got a data channel. They don't really talk to each other. It's not really an integrated architecture. And when you look at the system diagram, I think I've got a system diagram in this lecture, it looks a bit like somebody has sort of taken a voice architecture and just sort of bodged data on the side of it. There's quite a lot of that goes on in the mobile phone standard. 4G was the point at which people said, well, hang on, we've been packetizing voice for quite a while now, and when you make a phone call on a landline, your voice is digitized now quite early in the process and sent via your provider's network as a series of packets, special packets, which have to arrive in order and be put together properly. And 4G was the first system that did this. So it packetized the audio, and that has a lot of sort of architectural advantages. It means that everything's a data packet, and it's easier to build the system. And then 5G, well, we're giving this lecture in London, which is quite well 5G'd up. I'm aware quite a lot of the audience won't be living in London and perhaps haven't got 5G yet, but we're on the cusp of 5G. Those of us who are in London and think we've got 5G, well, I'll say a bit about that later, but you might think you've got 5G, but I doubt you've got 5G quite as it was intended. Now, what's been driving all of this? There's a sort of implicit assumption here that people have this craving for more and more data, and that's not a bad assumption, but that in itself has been driven by, I think, technological capability. So here's a fascinating sort of little comparison, which I found on the web and have adapted for my own purposes. So, well, let me tell you what these computers are, first of all. So on the left-hand side is a computer called the Cray 1 supercomputer. And it was getting a bit antique when I was a graduate student. I mean, I'm not that old, but it was very desirable to graduate students in computer science. We all wanted a Cray, And the way it's got this, it was regarded as well cool because you could sit around on its sofa. And when you went to a big lab, if it had a Cray, you'd sit on the sofa and go, "Ooh, it's a Cray." It was like a sort of Ferrari. It was the Ferrari of computers. Underneath the sofa or the couch down there is a compressor, and the compressor and it goes beneath the floor. So it wasn't when your estate manager didn't exactly bless you when you bought a Cray, because you had to dig a whacking great hole in the floor and get this thing in there, and the compressor kept it cool. They're often super cooled. And they're highly, highly desirable machines. The Cray one was the first one of these. It was very expensive. A bidding war broke out, I think, between the National Security Agency in the USA and one of the other scientific agencies, so the price was heavily inflated. They were desperate to get hold of it. And then the second one, this is the computer that beat Garry Kasparov. It comes in 2 cabinets and was really a logic engine. Maybe it's a bit unfair to pick Deep Blue. It wasn't really designed for doing the same task, but it was a benchmark computer. And I've just picked your average mobile phone on the right. This is an iPhone 13. Right, which one of these is the most powerful computer? That's the question. Well, I should guess everyone in the audience knows the answer. I mean, you can guess the answer. I bet you're all making the same guess. But what's surprising is by how much more powerful it is. So on the left-hand side, 160 million floating point operations per second. Now, there's always a bit of a debate about what we mean by a flop, but let's say it's a multiply accumulate operation. And over here on the right-hand side, 1,500,000 megaflops. It is staggeringly more powerful. I'm just totally flabbergasted when I saw this comparison. The computer in your pocket is literally a supercomputer of yesteryear. I mean, it's absolutely blindingly amazing. And that fact alone is worth just sort of pondering and reflecting on. The staggering increase in computational processing power associated with electronic devices in general has led to, really, the dramatic need for data wherever you are. So this is the key driver for the cellular revolution. Now then, buzzword bingo, or rebarbative acronyms. Now, one of the difficulties with this field is that the phrases 1G, 2G, 3G, 4G, 5G are very commonly used, and almost everybody does use them, but they're not used by the professionals. And why isn't that? Well, I don't really know why that is. I mean, but it's annoying. Let me try and explain how these standards work. And it's so complicated, I may run the risk here of oversimplifying. But the root of the standards is the ITU, the International Telecommunication Union. And they tend to specify what they would like to see from the next generation of mobile telephony. And they will use some acronym for it. So I've got 3 of them up here. 3G, they called IMT 2000, because I think they were expecting it to roll out in the year 2000. 4G was IMT Advanced. I can't quite tell you why they abandoned the traditional. I can make a guess, but anyway, let's not speculate on that. It's called IMT Advanced, and 5G IMT 2020. Then the business of developing the components of the standard is left to another group called 3GPP, which is a conglomerate of telecommunication standards agencies from across the globe. And then they work out what will we need to do in order to produce specifications that look like those that are described in the ITU. And usually they will split the standard into components. So the one that might look a bit unfamiliar to you is the RAN, right? The RAN is the radio access network. That's the radio bit of the system. And for 3G, it was called UTRAN. And what did UTRAN? Universal Terrestrial Radio Access Network. Very imaginative. And then we got extended UTRAN, EUTRAN. And then, fortunately, as we've got towards 5G, they realised the stupidity of having all of these crazy names. So we now have NR, New Radio. And that's the bit that covers the airwaves. Then we've got the bit that's doing the work. That's the core name. And then we've got the overall name for the system. And you can see, by the time we got to 5G, sense has prevailed, the 5G is the first mobile telephony system that actually is called 5G. That's a win, as far as I'm concerned. Now, what haven't I explained on that slide? I think I've gone through all of those acronyms, haven't I? I'm sorry, but it's acronym central when you come to talking about mobile telephony. The important thing is, and I don't want to skip this, I don't want to underemphasize this, there's an incredible amount, an intense amount of international cooperation in the construction of telecommunication standards. Even countries that are at war have to agree on how they are going to communicate. So postal telecommunications unions and so on are a very interesting form of diplomacy. And there's a whole lecture to be given, I think, about technical diplomacy, which is very, the world is immeasurably richer because of it, and it's very important. And I should point out that the 1G systems, we couldn't roam or do any of those things. So I don't know if anyone in the audience remembers these days, but if you went to the USA, you would hire a mobile phone for the duration you were there because you needed one that would work with where you were. And because the USA is such a big country, you'd need to hire one at the airport because it wouldn't necessarily work across the whole country. So we're now not in that position. There's now a lot of commonality. There's enough commonality across mobile phones that your phone can roam. Right, let's have a look at one of these standards. So let's have a look at 5G, because that's the one that's either, if you're hip, trendy person, you've already got a 5G phone. If you're not a hip and trendy person, you're probably, well, you might still be grubbing around with a 3G phone, but thinking to upgrade. So let's talk a little bit about that. So this is the way that the ITU has chosen to describe the two standards. It's a typically opaque diagram, and inside they have drawn for us IMT advanced, so that is 4G. Just check, yes, that's 4G. And on the outside we've got 5G, which is called IMT 2020. So let me just sort of read for you a few of the parameters of mobile telephony, because by thinking about those parameters we'll get a better understanding of what sort of matters with mobile telephony. So the first one that sort of strikes me is something called the peak data rate on the top left there, and that's measured in gigabits per second. So the one we're all familiar with, which is 4G, has a claimed peak data rate of 1 gigabit per second. Now, peak data rates, you've got to be very careful with that. It doesn't mean really in practice that my 4G phone ever was capable of 1 gigabit per second. In fact, I'm pretty confident I never got that. But what that means is if we were in the unusual situation where we had a phone with a priority SIM in it, and there was no one else in the cell, and the cell was properly connected with all the right equipment to a very fast backbone, then it might be possible to get 1 gigabit per second, provided you have the right phone, the wind was in the right direction and everything was quiet. Right? That's what we mean by peak data rate. Nevertheless, one thing that springs out immediately from this is that the new generation, 20 gigabits per second, that is quite a substantial data rate. So just getting connectivity to the base stations in 5G is a significant task. You can't just sort of plug it into any old internet that's skulking around, it's going to be fibre straight into the roadside cabinet, isn't it? Because that is a noticeable and very substantial rate. So if we think about the user experience data rate, which is more like what we've got, that's quoted at 100 megabits per second, so you can easily divide one by the other and find out a rather surprising number, which is that it sort of implies 200 users per cell. And you think, oh, that's not very many, is it? Only 200 users per cell? How does that work? And then, but, if we go down to the bottom, connection density, devices per kilometre, 1 million devices per kilometre. So what's going on there? Well, the standards bodies here are drawing a difference between users streaming data, and that's the people at the top, and users connected. So it's still a fairly staggering amount, isn't it? 1 million devices in a square kilometre. So a square kilometre, that's 333 metres by 333 metres. Could you really imagine 1 million devices? Well, 5G is rather unusual, and it has a set of use cases associated with it. So a use case is, for those of you who don't know, is a buzzword. It means an example of how this system might be used. And let's try and remember them. I'm sure one of them is a football match, where let's think of a football match. So the biggest stadium I could find is the Barcelona stadium, which holds 100,000 people. And the use case is everyone in Barcelona stadium wants to watch a high-definition video of the last goal, right? That's the sort of thing that would bring cellular networks to their knees. Now, I don't think 5G can cope with that situation, but could you imagine in that circumstance 1 million devices in a kilometre? Well, how many devices are on you now? Well, I've got my watch, and that doesn't speak 5G, but it probably will do. I've got my phone. Have I got anything else? Don't think I've got any other electronic devices, but I probably usually have 3 or 4. Oh, I've got my iPad, of course, yeah. So, well, I'm not particularly technology savvy, and I'm carrying 3 devices, and so that's easily, it will mount up. And one of the desires of the mobile phone infrastructure, new mobile phone infrastructure, is to provide connectivity not just to mobile phones. And in fact, mobile phones are not called mobile phones in the engineering standards for cellular telephony. They're called UEs, user equipment. And the idea is it might be a flood sensor, a bit of Internet of Things device. It might be some roadside cabinet monitoring something. 5G also allows for private networks. So it might be, you might have a whole bit of private 5G reserved for police communications or driving traffic lights, or something even more mission critical. I'll talk about one of the use cases later, which is a bit more mission critical. So there's a whole load of parameters here which are essentially to do with capacity. More people, more dense people, not I can say more dense people, but people more densely packed, higher traffic. 2 of them are perhaps a little bit less familiar to you. They're latency, that's how long you have to wait for the data to come through, and the other one is mobility. And I'll just park those for the time being and try and make a mental note to come back and talk about them slightly later on when we've talked a little bit about the technology that 5G has. Now, I haven't said very much about spectrum. There is an axis here called spectrum efficiency, and it is a fact that the radio waves in a lot of countries are getting rather packed. And one way of showing you this is to actually show you the frequencies that are in use or planned to be in use by country. So on the left-hand side here are a variety of countries, and running across the slide are increasing frequencies. So there are several interesting things about this. The first thing to say is that the 900 gigahertz, 700 gigahertz band is a sort of common feature in most countries. So that was one of the early bands that was released to mobile telephony. Now, the physical audience here today is probably quite familiar with the British situation, and the online audience is probably more familiar with the US situation. So I'll just try and talk separately about them because they're not the same situation at all. But in the UK, spectrum is heavily regulated by the government. So it's a fair bet. In fact, I think this applies to all the radio spectrum, that if you want to use a part of radio spectrum, then you need to have a license to do so. And these licenses can be bought from the government, and sometimes they're available very cheaply indeed. Low-frequency licenses are often reserved for low-frequency spectra, are often reserved for amateur use or naval use or maritime use. If you've ever used a marine VHF, there's an exam to use it, but it doesn't cost you anything to use it, and they're generally regarded as part of sort of safety infrastructure. The bands that mobile operators want to use, they were sold via auction, invented by a nameless civil servant in the UK, who decided it would be a good idea to sell off spectrum to the highest bidder. Well, it was very popular with the Treasury because huge sums of money changed hands, and as a taxpayer, I was rather pleased to receive my multiple billions of pounds from spectrum auctions. In the US, it's slightly different. There are some spectrum auctions. Some of the bands are controlled by government and they bring in a bit of money. And there are some uncontrolled bits of spectrum as well. And that's one of the attractions in the US, I think, of these higher frequencies. They're at the moment uncontrolled. In terms of cost, the general rule is, as we move across to the right of this slide, as the frequency goes up, the cost of the receiving equipment goes up as well. So there's considerable pressure to stay to the left in terms of cost, but the bandwidth goes up as well as we move up the spectrum. Bandwidth is a fraction of the carrier frequency, so obviously the higher the carrier frequency, the more data you can squeeze down there. But it becomes quite technically challenging to actually build the transmitters and the receivers. On the right-hand side, we're working at around a couple of millimetres wavelength, and on the left-hand side, we're working at sort of tens of centimetres. So the general rule is the antenna has to be a significant fraction of a wavelength in order to work. So the conventional mobile, sort of early mobile phones, have very small antennas compared to the wavelength. So they weren't terribly good and weren't terribly efficient at receiving things, so you had to have reasonably high signal strength, but quite good range. And then over on this side, the antennas are easily wavelength size and might even be larger, and that means they're getting quite directional, and we're really talking about line of sight communication and not much penetration through solid objects. So it's an incredibly wide sort of band over which you've got to operate. One of the consequences of the sort of unregulation of spectrum is that you can have clashes, and the current one is playing out in the United States. So if you're in the business of flying, you're probably aware that one of the ways your aircraft tells how high it is above the ground is something called a radar altimeter, or altimeter if you prefer. And radar altimeters work just there. So 5G is overlapping with US radio altimeters. So if you're flying to the USA in the near future, I would have a word with the pilot and ask him or her to use one of the alternative methods of deciding how far above the ground you are, or hope that you're landing in an area that doesn't have any 5G masts in that vicinity. I don't know how it's going to play out. There's a good old legal tussle going on at the moment between the mobile operators and I suppose it's the FAA, the Federal Aviation Authority. One sort of imagines that safety might win, but that it's perfectly true that aircraft do have other ways of telling what their altitude is, not least of which is GPS, of course, which we've talked about in previous lectures. Right. This is according to Qualcomm, who are one of the leading companies in mobile telephony, and it's as good as any. And what I thought I would do is just try and take you through some of these ideas, which are labelled innovations. Now, are they innovations? I think the answer is no. Almost all of these innovations are very well known in various ways. What is innovative is the way they are applied. And I'll try and explain how they're all applied. Now, you might be looking at this and feeling slightly ill. I mean, the language looks hideously technical, doesn't it, and rather off-putting. But actually, the ideas are really all quite simple. And I think I'll start with the two on the left-hand side. So Qualcomm have called this flexible slot-based framework and scalable OFDM-based air interface, which sounds brilliant, doesn't it? But let's just pause and then I'll explain what it's about. So what they're talking about here is something called multiplexing. And multiplexing is a word that means sharing a resource, getting more than one signal down a piece of wire or across a radio waves. That's what multiplexing might mean. And early mobile phone systems, and in fact the public telephone network, used a form of multiplexing called time division multiplexing. And it's a slotting system. And it's quite easy. So what would happen is your voice signal was cut up into slots, and the slots were opened, and you had, if you imagine, switches that sort of commutate like this, or travelling slots coming down a wire, and you say, well, you now have a few milliseconds or microseconds to use this channel exclusively. So you would stuff your stuff in, it get transmitted to the other end, and then you get the next slot. You stuff your stuff in, gets transmitted to the other end. Time slicing. It's called time division multiplexing. Some people make a fuss about the difference between time division multiplexing, which is the cutting of things into time slots, and time division multiple access, which is cutting things into time slots and offering different people use of those time slots, and when they're finished, reusing the time slot for someone else. I mean, I think we're all intelligent adults and we don't see much difference between that. The principle is time slots. Now, the nice thing about time slots, I suppose, is it's relatively simple to explain and easy to understand. You do have to have synchronized clocks both ends, which is a bit of a pain. And you have to be careful that the slots aren't too long, because you're going to introduce some unpacking problems, and your voice, if you're trying to transmit voice, isn't going to fit so easily. That's TDM, not tedium, but TDM. Okay. The other alternative, which is already used in most systems, is FDM, frequency division multiplexing. And what you do in frequency division multiplexing is you say, well, I've got this big frequency channel that I could use, but you are going to have this little bit here, and you're going to have this little bit here, and this little bit here, and this little bit here. And that's what's sort of shown on the diagram here. Those are the channels that are used by each one of the users or one of their data streams. And each one of these things is usually placed on its own waveform, a sine wave, a particular frequency, and they're usually, in the parlance, called subcarriers. Subcarriers because the big band is defined by a carrier, and then each one of these little slots is defined by a subcarrier. Can be a bit of a pain producing these subcarriers. Certainly it was in the original analog system, a bit of a nuisance. What has happened to some extent in 4G, but heavily in 5G, is a cool digital way of creating those carriers. And that's orthogonal frequency domain multiplexing. That's the off-DM part. Okay, so off-DM it's frequency division multiplexing done a rather fancy digital way. Now, if you are very interested in the way it is done, it looks a bit repulsive, but quite easy to explain. Over on here, what we've got are our various channels. These are going into something called it's actually an inverse fast Fourier transform here, and we're adding them up to here, and out it goes onto the antenna. And the effect of that is to create these very narrow band channels that are all beautifully locked together. So we don't have the problem that you would have with an analog radio, which is the crystal wanders and they overlap with each other. These are so beautifully locked together that the nulls from one channel completely overlap another channel. Now, how exactly that works requires a little bit of understanding of the Fourier transform, which, incidentally, is the subject of the next lecture, orthogonal transforms. So if you are really into, or think you might be into orthogonal frequency domain multiplexing, tune in to the next episode of Richard's exciting lectures on innovation. One of the great things about this is it allows, to use the phraseology of the last slide, scalable numerology. Now, the problem we've got is, if we just skip back yet another slide, is that wherever we are on the planet, we're going to have different channel configurations. So in 4G, and certainly in 3G, you've got this problem. How even do you number the channels? You've got to number them in a consistent way that your device understands. That's called numerology. So 5G said, we'll never keep up with this. People will always be developing channels, and Japan will do something different, and China will do something different, and so on, so on, so on. So we need a system that allows us to slot in our channels into whatever channels there are, and do so in a consistent way. So that's what they mean by numerology. The final innovation is to say, well, given that we've got a very variable load, we don't know how many people there are in a cell, we don't know quite what the country's doing on various bands, and the bands might change depending on where we are in the country, because this antenna's working on this band and they're slightly different channel. What we need is something that allows us to do very flexible frequency division multiplexing and time division multiplexing. So 5G does both, right? And it uses this orthogonal frequency domain multiplexing. Right. That's the first two innovations dealt with. Are they in any sense original? Not really, no. OFDM is used in digital video broadcasting. So if you've got digital television at home, most people have now, that uses OFDM. It's a very well-known technique, and it achieves good data bandwidth usage. So that's one of the reasons it's popular. Channel coding. I talked about it in this last lecture under error control coding. Every digital communications expert on the planet is using basically, or wants to use, either low density parity check codes, Gallagher codes, or polar codes. It's because they get much closer to the Shannon limit than anything else. They're a relatively recent discovery. So if you've got a legacy system, everyone is rewriting the standard to use these new systems. Is it innovative? Well, Gallagher codes, I think, date from the 1970s. So, no, not really. But fair dinkum, everybody wants to do it. It just gives you more capacity. So that leaves two. Now, they're interesting, right? Let's talk about the first one, which is, well, let's just maybe skip millimeter waves. Millimeter waves, they're just short radio waves. The advantage of short radio waves we've talked about, you get extra bandwidth. The disadvantage of them actually is everything gets a bit directional, and that all points to the idea of having to form beams, steer your waves into the right direction. So let's just have a quick look at one of those. This is actually a trial antenna. They don't look like this in the street anymore because they've got a cover over them, but if you rip the cover off, this is what you would see. This is an example, this is a test example from 2017, so quite a time ago. I think it was produced by Bristol University, Lund University, BT and National Instruments, and it was designed to test some of the capacities of these systems. And this is, again, a pretty old idea. It probably dates from, actually I don't know what beam steering really dates from, probably pre-Second World War. Very common in sonar. So there's two ideas here. The first one is that instead of having a continuous long antenna, we don't need to do that. We can replace it with little separate, or discrete as they're called, elements, and add them up. So if I did that, I had lots of little discrete elements, I added them up, then I would form an antenna which looks very much like the continuous antenna, and it would be tuned to waves arriving from this direction, the so-called broadside direction. If I add them up with a delay to account for the wave speed, then I could tune it to the end-fire direction. It's coming like that. If I tweak the delays, I can steer the beam where I like. That is quite a powerful concept. because it means when you get out your 5G phone and you start to want to communicate with me, I can steer my beam onto you, and you might also have some beam forming in your phone, and your beam might lock onto my beam, and then we can negotiate a frequency, and within the same cell we could be using maybe, well, normally you'd use different frequencies, but I think in principle you could use the same frequency to communicate within the cell. So I've got all of these beams pointing out into the audience, each one of you being individually served with the full capacity of the network. That's the power of beam steering. So that is certainly proposed, and that's technology. You can actually do more. I don't know if they do this, but you can also steer a null. So if you were interfering with you, just steer a null onto you so I don't receive you at all in that beam. So that's possible. You can also... now, beam steering in sonar is a bit of a pain because you've got to really put in delays. In radio waves, you can just get away with phase delays, and they're quite easy to implement. So implementing these phase delays is quite a practical thing. So if you've got a phone, a reasonably modern phone, it will have 4 little antennas here, and it will also steer towards the antenna. So you've got this. There's a sort of start-up phase when both of them go into a sort of sweep and try to lock onto something, and that's how you can achieve these data rates. Right, 2 final things that I want to talk about quite briefly. Latency. In that slide, there was something called mobility, and mobility is the speed at which somebody can move through your cell and successfully communicate. And one of the hidden problems with mobile telephony is latency. It can take a while for data to get through the network. And I put up this diagram, which, I mean, does it make you feel ill looking at it? It does me. I mean, when I first saw this, I thought, this is one of the most disgusting system diagrams I've seen. And this is 3G, the UMTS system. Just to quickly point out how it works. So this is your mobile phone, the user equipment, and there's a protocol defined here for communicating with your base station, called Node B in the parlance. This is the radio network controller, which is the box you find by the side of the road, and all of these protocols are defined over here. Voice goes this way, out here, and out here is data, and I can never remember what these stand for. I'll have to look them up. This is the Gateway GPRS support node here, and this is the serving GPRS support node, like these things mean anything. And this is a gateway mobile switching center, and this is a local mobile switching center. This is the record of users, tells you who's in the system, and these are replicas of these, which are the visitor locator records, which tell you who is being served by that network. So you don't need a degree in computer science to see how horrendous that is. Firstly, you've got voice going one way, you've got data going another way, you've got all these visitor records that have to be shuffled around the whole network, so you can imagine the trouble. You turn on your mobile phone, suddenly it has to find your record from wherever you are in the world, shuffle it around, get it down to the right place so that we know who you are. Then you dial a number, then it has to go to the RNC. I don't know what to do with that number. The MSC says, well, I've never heard of that number. I'll send it up to the GMSC. It says, oh, yes, I can route that for you. That gets routed and your voice gets connected. Meanwhile, on your GPRS channel, some data is sort of wheezing out under terribly difficult conditions. You're lucky if you've got any connectivity at all. Now, that's 3G. 3G is going out of date. 4G is not much better. You know, it's even more complicated in some ways. The reason I put this diagram up is because there's legacy in these systems. And you can see that legacy at the roadside. You know, you might think that you're looking at a 4G system, but you're probably looking at a 4G system with bits of 3G from the last generation. Now, perhaps I'm being a little bit cruel about this. I mean, I don't want to diminish the enormous amount of engineering and hard work that goes into this. And I was trying to find a way to give you the sort of enthusiasm that people feel for this. And I realised it was done for me by a most ingenious gentleman called Peter Clark, who's, as far as I can tell, drives around the United Kingdom making videos of 5G phone masts. And I think this is a fairly rarefied pleasure. I mean, his videos give me quite a lot of pleasure, but maybe I'm a strange person. But I will play you a little clip of them, ladies and gentlemen, and you can make up your own mind. I thoroughly commend his YouTube channel to you. The reason I wanted to play it is, one, it gives you an immediate impression of the enormous amount of investment required to put this together, and two, some impression of the intense complexity of weaving these various standards together at the roadside. So this is Peter.
From groundbreaking civil engineering in the pursuit of densification to a sea change in parameter strategy, what a year 3UK has had in 2021. Perhaps most outwardly visible have been the hundreds of 5G Phase A unilateral poles 3 have been deploying around the country. Primarily, these have been entirely new locations. However, some of them have been in-place upgrades, like the pole behind me here. These poles of wonder are a key facet of 3's gigabit vision of deploying high-speed connectivity both to mobiles as well as households. However, getting these poles into the ground is anything but straightforward, and a substantial engineering effort is going on to get the thousands deployed that 3 aspires to have. To date, this has included over 3,000 planning applications, which I have tracked and then followed up, as well as large amounts of contractor and subcontractor activity.
Imagining tracking 3,000 planning applications just because you're interested in the matter. There's something that's not quite evident in that video, but I'd like to just end by pointing it out, which is you may have bought your phone assuming it was 5G. I mean, I have a phone here, which we're in the City of London, there's plenty of 5G around. In what sense is it 5G, though? That's the question. You know, does my user equipment have a beamform 5G antenna in it? Probably not. I know it doesn't. Because 5G and beamformed antennas weren't around when they made this phone. So it's using a 4G antenna and it's writing 5G on the top of my phone. So it's using some of the aspects of 5G, but certainly not. Is the 5G radio access network connected in standalone mode, meaning it's got all of those bandwidth capabilities, or is it bodged to an existing 4G network? Because the 5G standard allows you to bodge 5G radio access nodes into 4G. It's almost certainly bodged in for the time being. I mean, it won't be, it will change, but it isn't, you know, at the moment. So does it meet any of the requirements from the ITU for 5G? No, it can't do. You know, it's in bodge mode. So does it outperform my 4G phone? Well, actually, it doesn't seem to. You know, it's got a whole load of latency issues and blockage issues which are caused by being bodged into the 4G network. Now, this is a bit of a problem, isn't it? You know, you've got a phone that says it's 5G, which isn't acting like a 5G network, a 5G phone, connected to a network that says it's 5G that isn't and cannot act like a 5G network, being sold to you on the basis that it is 5G. It's not easy to measure the data rates on these things. So the sort of assumption, at least in the United Kingdom, which is that high bandwidth will drive a market, isn't really working because there's a bit of a badging issue. So I don't want to overemphasize that problem. I mean, it's still a bit of a masterpiece, but this badging is a problem, and it arises from the fact that the standard has to be highly dynamic to accommodate the local facilities that are available. In terms of a summary of what I would say about mobile telephony, the first thing is that mobile telephony has hardly any telephony in it at all. When was the last time you made a phone call on your mobile phone? I looked at my log and I think it was, well, ignoring Tesco's delivery drivers complaining that I wasn't home, I mean, probably 3 months ago, I actually initiated a phone call. I mean, I use my phone all the time. I didn't use it to make a phone call. I think it's a massively important innovator for technology, and we saw that in the amazing power of those devices, but it is a tangle of complicated standards, and you're either the sort of person who delights in complicated standards and regards it as the richness of humanity, or you're someone who feels slightly queasy, and in which case you'll have to wait a few years for 5G to really come. In terms of what's coming next, you will have heard me refer to in several of these lectures these important integral transforms, and I think it's time to get to grips with those, and that will be the topic of the next lecture. Thank you.
Well, thank you very much, Professor Harvey. We are going to sneak a few questions in, if we may, at the end. I've got a couple from the online audience. What is your view of the convergence between 5G and Wi-Fi?
Well, they certainly are converging, and that is one of the... that's a great question, because I should have mentioned it. So there's technology convergence, meaning some of the things I've been talking about, namely beamforming. Did I say it was called MIMO, multiple input, multiple output? Because each beam can cope with a different person. MIMO is certainly a feature of latest Wi-Fi standards, and one way of looking at Wi-Fi is just sort of infilling the bits of 5G that you the bits of 5G coverage that you can't easily get, namely in your home. So the problem, of course, is the telecommunications companies make quite a bit of money out of us using their network. And that is one of the things that 5G is slightly designed to address, because not only is 5G designed to provide private networks for people, it's also designed to produce networks that might be doing mission-critical things where perhaps you really need a QoS, a quality of service, that's far beyond what you would get from any public switch telephone network.
Thank you. One more from the online audience, and then I'll open it up to the in-person audience. This last one, with reference to 1G, could I ask if this was a development of the radio telephone as found in some of the upmarket cars of the 1960s, which I remember as a boy, the enabling of equipment took up half the boot of a large car?
Yeah, I remember them as well. There was a system, I can't remember who did it, but in Britain, you were exactly right. If you were very wealthy, you could afford a Jaguar with this radio telephone in the rear seat. The problem was there were only 3 or 4 radio masts, and there was one on the way up to Heathrow. It was low enough frequency that you could it was absolutely hopeless. So people would deliberately postpone their calls so that they could call someone for the prestige of saying, I'm calling you from my motor car. It's absolutely crazy. I remember being rung up in the middle of the night by someone from the back of his car saying, I've got a phone in my car. I said, well, I haven't got one fitted to the bed yet in my pyjamas. I don't think that really counts as cellular, that what was happening there. I don't think that claim is good enough. They were just radio telephones. They're just like military telephones. The important thing about cellular is this detailed handover procedure, and that was the technical innovation that existed in cellular. So radio telephones, old idea. Cellular was the infrastructure and the standard to put them together. Radio telephones with no standard for connecting them, they're just radio telephones. They don't change the planet.
2 questions, really. One, I listen very often to the Today programme on radio, and it very often features phone calls, which increasingly become difficult to connect. Do you have any comment on that? And the second question is, when you were comparing the power of various computers and saying that a particular mobile phone was it 1,500 gigaflops, does the mobile phone really need floating point operations anyway? I regard them as important for scientific calculations, but I don't see any purely scientific calculations being done in a mobile phone, but perhaps I'm wrong.
Right, so shall I take the hard one first, which is about flops? You're quite right, I had to pick something, and I just picked flops as a sort of generic indicator of performance. And it's certainly true that, for example, the most powerful criticism, let me make a more powerful case for you, which is you wouldn't really measure deep blue by flops because it didn't really do many floating point operations. I just picked a number. That said, I think you're wrong in assuming that a modern mobile phone doesn't do a lot of floating point computation. I was sitting on the tube this morning and everybody in my tube was running massively parallel, massive amount of floating point computation on their phones. They were actually getting hot doing it. They were playing games. So that's the thing about a phone, is it's not really a phone. It's a machine for doing stuff. And what was the first question? I've forgotten.
About the Today programme.
Oh, Today programme, yeah. Well, okay, so here's an interesting thing. The quality of connection on mobile phones is not as good as landlines. It can't be, because you've got this, one is, you've got all sorts of problems that you have to contend with. The first one is handover. If you're moving, you might be moving between cells. If you've got beam forming, well, somebody else has arrived and we've got to reform a beam for them and it might clash with you. So there's all of that going on. That's one issue. Then we've got fixed capacity issues in cells. No more people can be accommodated. So I didn't mention, and perhaps should have done, an alternative idea that was used in the US for a while, which is code division multiplexing. And the idea there is you're all given your separate code and it sort of fails soft is the idea. As more and more people speak, the noise level goes up and the interference goes up and it sort of gently declines. It didn't work out like that and it had a hard threshold and died on you. So there's every reason to think that mobile telephony cannot be as reliable as wireless telephony, that's for sure. And that's without the issue of voice quality, which should be now very similar. So the voice quality should be very similar to a landline, but the connection cannot ever be as good as a landline, I think.
I'm so sorry, everyone. We're going to have to draw it to a close there, I'm afraid. We've gone over a bit, but thank you very much for coming this evening. Thank you for your attention, and to our online audience as well. Thanks for your attention, and please join me in thanking the professor for his lecture.